Welcome, everyone. Good morning, good afternoon, or good evening, depending upon where you've joined us from. We'd like to, first of all, just remind our speakers that this session is being recorded. We invite you to submit your questions by the Q&A button. You can find this button at the bottom of the screen. We'll address your questions as much as possible after the talk or during any Q&A sessions. And you'll see each question once it is answered either verbally or in writing when they will be displayed for everyone to see. Now we have a very large audience and we may not have time to answer all the questions live, but we'll aim to collect written responses from presenters to place on the conference website following this event. Please note the chat box is disabled during the session. However, we'll ask to keep an eye out for any useful messages that may be shared in this box from the organizers and moderators. You have the option of switching to automatic subtitles at the bottom of your screen if you have hearing difficulties. And if you experience any technical problems, please contact the Zoom Help Center or send an email to the online conference for assistance. We would like to today start off this session on emerging contaminants in groundwater with the keynote presentation by Dan Lapworth from the British Geological Survey. He'll be speaking on emerging contaminants in groundwater and improving the evidence base to inform policy and regulations. Thank you very much, Dan, and we look forward to your talk.
Thank you, Bob, for that warm introduction, and thank you for the organisers for giving me the opportunity to share a little bit on this sort of whistle-top tour, really talk on improving the evidence base to inform policy and regulation, in particular relevant to emerging contaminants. Next slide, please. Hardly a day goes by when we don't hear some sort of news story being published in the press or in scientific journals, or indeed catching our attention through the media and films on this topic of emerging contaminants, be it contaminants such as perfluorinated and polyfluorinated organics, microplastics, or indeed the issue of there being a cocktail or mixture of a diverse range of emerging contaminants affecting our groundwaters and rivers. However, there's an important issue. Many of these contaminants are not particularly well understood within groundwater systems, and groundwater systems need greater protection. In many settings around the world, groundwater is the only available water resource, and often the case it's sort of the resource of last resort, and has the highest quality potentially, but it's potentially threatened from a cocktail or potentially a time bomb of a range of different emerging contaminants that can threaten groundwater quality. Clean groundwater is key for a healthy and resilient environment, and groundwater protection is obviously better than remediation. So that's why this topic is so important. Next slide, please. So what do we mean by groundwater contaminants of emerging concern? So these are anthropogenic contaminants, largely organic compounds, as well as their transformation products. They can also be anthropogenic particles, so these may be plastic particles or other engineered particles. And they may also be microbial contaminants of emerging concern, for instance, viruses or antimicrobial resistant genes within the groundwater system. They're often considered, a range of different contaminations from a range of sources, so there may be a mixture of different contaminants, and are often described as a cocktail of different contaminants that may affect groundwater from wastewater sources. And emerging contaminants have clearly a different profile compared to surface water contaminants due to their subsurface transport and residence time aspects within the groundwater system. So what we see in surface waters may not necessarily translate to exactly what we see in groundwater systems. And emerging contaminants emerge as a result of a range of different processes. So changes in the use and manufacture of products that we use as society, changes in the techniques that we can use to detect them, as well as improved monitoring. And groundwater contamination is generally much less well characterized compared to surface waters. And there are a range of different sources. The diagram on the right-hand side just gives you a few examples of different anthropogenic sources and activities at the surface that may contribute to a range of different diversity of different emerging contaminants. and how they may move within the subsurface to affect groundwater systems. Key sources of these include groundwater surface water interactions, of course, as well as things such as managed aquifer recharge, which may potentially bypass sort of natural protection if it isn't managed correctly, as well as sustainable urban drainage systems to enhance recharge, which may again bypass natural barriers within the subsurface. So the point to take home is that there are a huge diversity of different types of surface activities that can potentially pollute groundwater systems. So next slide, please. So what's been done on this topic so far? Well, quite a lot, really. There's certainly a growing evidence base for emerging contaminants pollution globally, driven by research activities across the world, but also by kind of more formalized surveillance monitoring by the water sector. And there have been several regional initiatives to try and improve monitoring of priority emerging contaminants in groundwater. And a good example of this, which I'll share a little bit more about in the subsequent slides, was the first European groundwater watch list, which was developed 5 or 6 years ago. On the right-hand side, we can see a few examples of these, so sort of national monitoring programs in England, looking at emerging contaminants such as caffeine. We've got, to the right of that, we've got a kind of conceptual model of how perfluorinated organics may be transmitted and move in the subsurface. We've got below that, we've got a conceptual model that was developed by Veroli et al. Recently, which looks at how microplastics, different sources of microplastics, and how these may move in the subsurface and the different routes to groundwater within groundwater systems from a range of different sources at the surface. And then to the left of that, some work that we've been undertaking in India, looking at a range of different antimicrobial agents and other emerging contaminants in groundwater systems beneath urban settlements in Varanasi and Bangalore in particular, and how these vary with depth. And this topic has become a high priority for a range of different stakeholders. You know, regulators, the water industry, and in particular wider society are particularly interested in the occurrence and risk posed by emerging contaminants. And there's a growing focus, be fair to say, on a selected number of these emerging contaminant groups. Perfluorinated compounds have a particular focus at the minute, and are sort of certainly being looked at in great detail by the water industry. Plastics is another area which has generated a huge amount of interest, but also pharmaceuticals and antimicrobial resistance is also developing a kind of a profile now, and is a growing focus for research and also monitoring activities. But we need a coherent approach to the protection of groundwater from key priority emerging contaminants, and stronger policy to change how society views these types of chemicals, and also how we think about monitoring them now, the ones that are a risk for us now, but also those that may come along and be a risk for us in the future. If you could move to the next slide, please. So this is just a couple of slides now to sort of share with you a case study from related to the European Groundwater Watch List. So this is the figure on the left-hand side really just shows you a chronicle of where this watch list emerged from, the legislation that emerged from, and the kind of long journey it went through different steps, both through EU formal EU regulation, but also how research and various initiatives within the European Union sort of help focus attention on emerging contaminants. So we can trace its roots back to the Water Framework Directive back in 2000, but it was really kick-started in 2014 through the working group of the Common Implementation Strategy, working group on groundwater, which agreed in principle for a groundwater watch list, and there was a call for evidence, and a range of different national agencies contributed to the evidence base, and through a collaborative partnership across Europe, working together with about 12 different countries across Europe. Gradually, evidence on a range of different emerging contaminants was brought together. Pharmaceuticals and PFAS contaminants are clearly prominent within that, and developed what was, in effect, the first prioritization list and watch list for emerging contaminants, with the view that in the future, if this voluntary initiative was a success, it would then be adopted subsequently within formal regulation, and this was initiated in 2014. This was published, this particular article I'm referring to here, in 2019, and they're just going through the process now of actually updating the Groundwater Directive to formally implement emerging contaminants. So it's been a long journey. But what's interesting is, can this type of approach, voluntary initiative, work in other regions? And how do we ensure that the evidence base on this type of information is shared more effectively in the future, particularly when many of these contaminants are widespread and global and not just a concern within Europe? And there's certainly an ongoing need to prioritise hazardous groups and improve monitoring. But there's this tension between the need to do that, but also the need to have sufficient evidence with which to underpin the regulation if that actually gets formalised. So next slide, please. So what are the core principles of the European watch list? Well, first of all, developing a conceptual understanding and approach to how contaminants migrate and what the sources were. And then second phase, prioritisation approach, which is really the core aspects of the groundwater watch list. It was to produce a dynamic list of compounds of around 10 to 15 compounds, striking a balance between the need to safeguard groundwater, but also the need to not increase costs in monitoring and analysis too much, and to not put too much burden on the water sector. To prioritise based on existing monitoring data, on exposure and mobility data, but also particularly on toxicity data. This is a multi-stakeholder initiative involving a range involving business, involving regulators, and involving research stakeholders. So next slide, please. So what are the next steps? Well, there's certainly growing awareness within the research community and wider society of a potential sort of harmful cocktails of emerging contaminants which can pollute groundwater. And we need to improve the evidence base and monitoring to inform policy and regulation in this area. And in order to do this effectively, as has been demonstrated through the groundwater watch list recently, we need to involve a number of different stakeholders to work together on this and to build a resilient framework for monitoring priority emerging contaminants in groundwater and reduce impacts from these contaminants. And as part of that, there's a range of sort of building blocks that we need to think about, or approaches that we need to think about and include to make this effective. So the solutions and objectives of the prioritization process or the monitoring, the watch list needs to be pragmatic. It needs to include a wide consensus among stakeholders, both within industry, the water sector, and regulators. It needs to be achievable within a realistic time frame. So not over ambitious, but starting slowly and starting with something that's achievable. And it needs to be formulated in a way to have a lasting legacy, to actually be implemented and be adopted more formally. The groundwater watch list started as a voluntary initiative and is going to be formally adopted quite soon. But starting as a voluntary initiative was an important first step in this process. For example, we need to harness the knowledge and motivation of a wide range of stakeholders to make this work. We need to continue to promote best practice, both in terms of monitoring practice and analytical capabilities, in order to make this effective going forward. And we need to consider the full cycle of emerging contaminants and their use by society, if we're really going to get to grips with the range of potential emerging contaminants that are with us now, but also may be with us in the future as we develop as society. So if we can move on to the next slide, please. So I've finished a little bit early, a minute or so to go, but thank you for listening. And thank you for giving me some time and this opportunity to share with you a little bit about the different types of emerging contaminants, but also, if you like, a recent success story on how a voluntary initiative like the Groundwater Watch List has been formally adopted within, or is starting to be formally adopted within European regulation and monitoring, which may be an example of how we can move forward with this type of contamination issue in the future. Just leaving you with a little cartoon really about perfluorinated organics and the complexity of this particular group of contaminants and its threat to groundwater. Well, thank you for your time, and that I'll leave it at that.
Thank you very much, Daniel. That was very informative. I would like to hand over to our co-moderator today, Malcolm Gander, who's going to lead some question and answers. Remember, there's the Q&A box there. So Malcolm, if you could possibly lead some Q&A session, please.
Yeah, very good. We've got a question here. First, it's from the Minister, Reina Solitan Sotillo of Argentina. And congratulations to Dan, thanks oil to prevent movement of the contaminants. Are inductions of chemicals or biological reactions favorable to neutralize or immobilize contaminants? You can comment on that, Dan?
Yeah, should I answer that now or should I type in my answer?
You can make a few brief comments. No, I think
okay, we've got time to make a few comments. Okay, yeah, absolutely. There are certainly favorable conditions within many aquifer systems to help, both through chemical and also through biological reactions to neutralize or reduce some of these contaminants and reduce their concentrations. But many of them, certainly the ones that we're particularly concerned about, are actually quite persistent. So they do actually bypass many of their natural biological breakdown mechanisms. And a good example of that are PFAS compounds, are particularly persistent, particularly toxic group of contaminants. And then many other contaminants, I think it'd be fair to say that we still don't know. For instance, microplastics and nanoplastics, we don't really know how like microbes interact with these particular groups as yet. The sort of evidence base isn't there yet. And also we don't really know how they are transformed and modified within the subsurface by bacterial activities or chemical activities on the surface of these types of particles. So there's a lot yet to be understood. But some, yes, some are modified naturally, but others are particularly persistent, and yet others we don't really know quite what their fate is yet. What's the next question? So what are your thoughts on differences in areas of the world that are different?
Yeah, Michelle Embry is wondering, what are your thoughts on the differences? Go ahead.
So I guess this is partly an issue to do with the nature of groundwater having a range of different residence times depending on where you are within the aquifer system, and also where you are in relation to a particular contaminant source. So what may be emerging in one area may not have yet emerged in another region, and what may have actually been and gone may still not have even arrived in some areas, depending on where in the aquifer system you're abstracting and looking, and also where you are in terms of its relation to the source of contamination. So it's you know, it's this inherent complexity of the groundwater system, which means that we have a real range, a continuum between contaminants that are emerged, if you like, in some regions, fully or starting to be understood in a lot more detail, and also those which are as yet still truly kind of newly emerging and are being investigated in earnest at the minute. It'd also be fair to say that, you know, the evidence base is quite biased to certain regions within the globe, and we don't really know how many of these contaminants, their occurrence, how that is, you know, where they are in the subsurface and in what type of concentrations in many other regions where they haven't been investigated yet. So it's fair to say that whether a particular contaminant may be well understood, or people may think they understand it quite well in some parts of the world, it hasn't really even started to be investigated in other parts yet. So there's that real discrepancy in terms of our level of understanding as well. Jason, what's yours question? So far, what specific ECs are currently determined as high priority? And are we familiar with the behaviour now such that we can incorporate the behaviour in groundwater models? The specific ECs that are currently determined as high priority are those with particularly high toxicity. So those are the hazardous to either ourselves or to other ecosystems that are dependent on groundwaters. So that's really the, if you like, the way that the ECs are prioritized. Some have been included in some modeling studies where we know the kind of physical and chemical properties and behavior, and we have some idea largely through lab experimentation and smaller scale experimentation what their fate may be in the subsurface. But it'd be fair to say that, you know, so that may include many pharmaceuticals that have been looked at in some detail, but there are many groups of ECs where we don't really have that baseline information yet. So going to the stage of modelling them would be a little bit ambitious and would require a lot of assumptions, I think, for many of them. Caffeine is the caffeine monitoring primarily to track contamination of domestic effluent? Yeah. Yes, to some extent, although I mean, caffeine's quite a good tracer in the sense that it's relatively quickly broken down within the environment. So it has a relatively short residence time as a tracer. So it's quite good for tracing proximal sources and sources which maybe have groundwater sources that maybe have a close connection with, say, surface waters, so like Karst systems, for example. The types of emerging contaminants you spoke of, are these found in groundwater in particular regions, or would you say they are a global occurrence? So the ones I referred to, I would say are of a global nature. So no, you know, we use plastics, we use pharmaceuticals, we use perfluorinated compounds in all sorts of products as a society, and these are used across the world. These are not peculiar to Europe or North America. These are truly global contaminants, and that's one of the reasons why people are so concerned, because they are so ubiquitously used and in demand by society and used for a range of different products that we use every day.
Okay, Dan.
I think
if you could take the time to answer any other questions in the chat box, that would be very helpful. I mean, in the Q&A box, that would be very helpful. And I'd like to thank you again for a very informative presentation and information and answers to a wide variety of different questions.
Thank you, Rob.
We would like to move on to the next speaker, Eliana Munarriz. She'll be presenting on how to prioritize agrochemical pollutant evaluation in drinking water. Looking at the Risk 21 tools, do they provide a framework for chemical risk assessment? So Eliana, the floor is yours.
Thank you very much. Good morning, good afternoon, good evening to everyone. And I would like to thank the organizing committee to give us the chance today to talk about the RIS-21 web tool and how it can be used to provide a framework for chemical risk assessment in water. Next slide, next please. So before going to the science, I would like to tell you about the Health and Environmental Science Institute, or HESI, that is the institution that developed the RIS-21 web tool, which mission is to identify and help to resolve global health and environmental challenge through the engagement of scientists from academia, government, industries, ONG, and other partners. And the way that HESI works is through global committees. There are more than 25, and these committees work in developing decision frameworks and sharing and working with collective data, write papers and publish novel experimental issues, prepare tool and sales, and also organizing scientific meetings and trainings worldwide. So if you are interested in this organization or think that it can be useful for you, please check the HESI global website. Next, please. So RIS-21 came from risk assessment in the 21st century. And as we were speaking about, we were listening before about hazard and exposure. So risk is different from hazard and exposure. It's a function between the hazard and the exposure. So it's the probability to have an injury or an illness resulting from exposure of a potential hazard. So RIS-21 is not only the web tool, that is the matrix that you can see on the right side of the screen, is also a conceptual framework which help us to use to have an effective use of relevant information to have an evaluation of the sufficiency of exposure and hazard information to make a decision based on risk. And it have different steps, the particular 4 steps. I'm gonna try to walk you through this one in a very simple and easy way in this short talk. So we use this approach to help them to collaborate with the health ministry in Colombia to ask a specific question that they have. Next slide, please. So before going into the project, RIS-21 at the end, after giving the information regarding toxicity and exposure, you have the result that is this matrix. Obviously, it is exposure and toxicity. So more red it is, more risky is that compound, and more green it is, more safe. So it's very visual. It has been used for different applications like experimental designs of screening or prioritizations of pollutants or any other application. In this project, we use for sort of a mix of prioritization and categorization. But the most important thing that RIS-21 is taking advantage of the existing information and help to identify if any additional information is need to make a decision regarding a chemical risk in assessment for in water or in any other environmental or matrix or health, human health also. Next, please. So today I'm going to talk about how we use RIS-21 with real data from a Colombia region, that is the region of Chiquinquirá. It's a typical agricultural region, and agrochemicals have been used, all sorts of agrochemicals to increase the productivity. The Ministry of Health was interesting because all these agrochemicals obviously go into the water, and then from surface water and also groundwater, they take this water to the purification plants and give the access to drinking water for the people of the region. So next slide, please. So the aim of this analysis was to evaluate which of the most commonly used insecticides that were used for potato crop in this region in Colombia should be prioritized for more monitoring or further information basing of the potential risk to human health through the exposure via drinking water consumption. Next, please. So here are the pesticides which we use for this study. There have been used for more than 5 years in the region. As you can see, there are very well known. Probably most of you listened at least at that of this one. But the most important thing that there is available data and reliable study, no, because farmers are using it, so it's available to anyone. So you have physical, chemical properties, environmental fates, toxicity studies. So we use this data that is already generated to answer the question that the health ministry need to address. Next slide, please. So the first step of the RIS-21 concept of framework or idea is that you need to make a problem formulation statement. The problem formulation is that really focusing which data do you need to address your question. Okay, so HESI has also a tool that helps to walk through this process. That consider exposure media, routes, and receptors. I'm not going to go through this one, but at the end of the problem formulation is really think about what you need to assess. Okay, so to have a bottom line, and the bottom line was to identify which insecticide need to be further studied in this region. Next one, please. So which factors impacting the pesticide exposure? We have several ones like pesticide properties, and also the rates of the application, the irrigation, and all this is accessible information. Next slide, please. So also we have the label of the pesticides that give you an idea of the application rate and the concentration. And all the other information is very accessible. Next slide, please. So then we use Indian exposure web tool that is free also. The idea is to develop this and doesn't have any cost for the person that does it. This is has been developed from CropLife and it's accessible online. So it has very simple inputs, and at the end it provides you with estimate environmental concentration, and this estimation environmental concentration is the one that we use to estimate the human exposure by drinking. Next slide, please. Regarding the toxicity data, as are well-known pesticides, we have studies, we have the toxicity, we have the NOAEL, and we applied an uncertainty factor to obtain the dose of reference. Next slide, please. So with all this data that we did not generate, we just have all the information in the web or talking with the authorities, we go to the matrix, to the RIS-21 matrix, and did the plot. So exposure, we use the EEC, the estimate, and we put in the worst case scenario that the person drink it straight to the source, drink it straight from the river. That is almost very, very unlikely. And obviously for the estimation, we consider 2 liters a day and a person of 70 kilos. We put an uncertainty factor and that gives us the exposure. For the toxicity, we use the NOAEL factor plus the uncertainty factors also and give us the range of toxicity. Next slide, please. We did our calculation. Sort of the conclusion, or what I want you to focus on the bottom line of this talk is that we need to make the prioritization in water basin of risk. Because if we do it only on hazard, that is the one that you can see on the left, you have if you look only at the toxicity, you can have a different output. And really you need to have on risk when you need to evaluate also the exposure. So RIS-21 is a specific and very useful tool for this because it's accessible, it's free, it's user-friendly, and it can help a lot the regulators for policymaker and risk and chemical risk management. Next slide, please. And this is my last slide. So as a conclusion, I would like to share with you that the work that I present is only for chemicals, but this paper has been published and a similar work has been done with more than 400 chemicals to have the prioritizations in drinking water in Canada. Okay, so just as a bottom line, the RIS 21 brings authority, a coherent science-based decision-making tool, easy to handle and to communicate potential chemical pollutant risk, contribute also with the governance process to set a priority set and analyze of potential future scenarios of chemical exposure and environmental for environmental and human health analysis. Next slide, that is the acknowledgement, please. Okay. And just I would like to thank all of you, first of all, and then the people from the Health Ministry of Colombia, the people from the university, also Ariana Rosen from the National Institute of Water of Argentina that have been involved, and especially to Sandrine and Michelle Embry, that is the deputy of HESI and Silvin. And if you have any interested, please do not hesitate to contact me or Michelle. Thank you very much.
Thank you very much. Thank you very much. We'll move straight on to our next talk by Rachel Kaiser. She'll be presenting on understanding the prevalence and occurrence of antimicrobial resistance in urban karst groundwaters. Thank you very much.
Great, thank you. So yes, welcome all. And I'm going to be presenting on a portion of my dissertation looking at antimicrobial resistance, or AMR, in urban karst groundwater systems. So next slide, please. So just to start it off with a little bit of background on why this is relevant. So AMR is a global health crisis that is impacting human, animal, and environmental health. Specifically, it's estimated there's about 700,000 deaths annually as a result, as well as over $100 trillion in productivity losses globally. So research is really focused on human and animal health, with the environment considered least in comparison. And within that, water resources. So within those resources, wastewater has received a lot of attention, as well as drinking water. But environmental source water, particularly groundwater and karst groundwater, tends to be overlooked, even though this is a concern because water resources are considered our primary environmental reservoir, as well as dissemination pathway. And it has been noted that the groundwater is a global reservoir for AMR, particularly with providing a buffered environment, as well as allowing for vast dissemination throughout these aquifers. And then considering karst, which is a subset of groundwater, these are unique because there's little to no natural filtration between the surface and subsurface in these areas. And also these groundwater systems supply almost 1.2 billion people with drinking water. So knowing that there's AMR here is a concern and a threat to public as well as environmental health. So my purpose is to understand the occurrence as well as dissemination of these contaminants within urban karst groundwater systems. So next slide, please. So I targeted two varying urban karst areas, Tampa Bay metropolitan area in Florida, which is a developed urbanized karst area, and Bowling Green, Kentucky here on the right-hand side, which is a developing urban karst area. Both of these have mixed land use between agricultural, residential, and industrial, but they're primarily impacted by urbanization. Next slide, please. So with these, I first looked at antibiotic-resistant bacteria in both Kentucky and Florida. As you can see here with these pie charts, there was a ubiquitous presence of these resistant bacteria for both Enterococcus and E. coli indicator bacteria. And the genes that were targeted are primarily associated with urban or clinical practices for macrolide, tetracycline, and beta-lactam resistant antibiotic types. So this is Kentucky, and next slide, please. And there were similar findings in the Florida study area, even though there are different types of karst as well as different urban areas. So we're seeing that these are spread throughout these urban karst aquifers, regardless of mixed land use. So we're seeing that there is that human and urban input to these AMR here. Next slide, please. So then I took that a step further and looked at antibiotic resistant or antimicrobial resistant genes that are related to these human and urban and clinical practices, as well as microbial source trackers, looking at animal as well as human fecal indicator waste. And so within those in Kentucky, as well as in Florida, next slide, please. Just to kind of show you Florida sampling as well, we do see that there's a prominent occurrence of these human MST markers within these systems. So we again are seeing that there is this urban influence with the bacteria as well as the resistant genes present there. And then even though there is mixed land use within these recharge basins, we're seeing that there's potentially a constant source and input of human waste contributing to these AMRs. And then within these systems too, we're seeing that regardless of the Karst feature type, there's kind of an accumulation as it moves through the system, since the springs are kind of capturing the highest abundance as well as occurrence of these genes throughout the system. And this is concerning because these are primarily used for drinking water resource if groundwater is used, but otherwise these feed into surface streams, which are also contributing to drinking water. And these are not regulated. So we're seeing that this is being introduced in kind of out of sight, out of mind mindset here. So next slide, please. And so overall, we're seeing that these are a threat to human health as well as environmental health, and that they are disseminated throughout these aquifers, regardless of the input source. There's a constant occurrence of ARB and ARGs despite seasonality. So this groundwater is providing a buffered environment, allowing for this consistent presence to occur. Within Karst systems, the feature type as well as temporal parameters are potentially driving this development here. And overall, there's a need to monitor and regulate resistance within groundwater, but specifically urban Karst groundwater systems. So, thank you.
Thank you very much, Rachel. That was an excellent presentation. We move on next to Rosa Leo Bautista, who will be talking about the assessment of emerging organic contaminants in the groundwater of Yucatán.
Okay, so one of the projects that we've been doing, and I've been working with Dr. Bautista in Mexico for many years, is looking at emerging contaminants in groundwater in the Yucatán Peninsula. Rachel did a great job of talking about Karst situations is what we have in Mexico. Next slide. So the Yucatán Peninsula, like Florida and Kentucky, is a Karst. One of the big differences here is that this is predominantly done with tourist activities. So it is one of the largest drivers of economics in the country of Mexico. And the population growth is tremendous in this region because of tourist activities. And there's also a Maya train that's going in. So they're building a train, and here she is, that is connecting the Campeche region and connecting the whole region, which will have a major impact on the groundwater here. Next slide. Rosie, if you're available, you want to give the talk now?
Thank you. Sorry about that. Yeah, it was a loss of connection. Yes, it's because Yucatán Peninsula, as Melissa just mentioned, is an area where not just the activities that are growing and rising really fast, but also the vulnerability of the Karst situation, as just the presenter before mentioned. And now these are the conditions that we have. We have one of the most open, which happen to be the only groundwater reservoir peninsula. So we are talking about we are groundwater dependent ecosystems, but also the rest of the activities are going to be related with how much we have of water, but in which quality we use it. So that's why we have this big concern. The other situation is we don't have rivers, we don't have big lakes, we just have this fresh groundwater that is floating above saline groundwater. So we have also a problem with saline intrusions. And we have the main activity related with touristic recreational activities, but a growing population that is going to be the double for the probably in the next 10 years. So 10 years, we are looking forward to see a rise in contamination in the area. Next slide, please. Thank you. So why we choose emerging contaminants to start evaluating what the conditions in the groundwater here? Well, it was exactly because it's useful for the monitoring of the behavior of wastewater treatment plants, and also to relate with how much it was coming from the tourist activities and from the locals. So we start checking into the pharmaceuticals and also different antibiotics and personal care products that have been using for bathing and swimming. Next slide, please. So where we have been evaluating this situation? Well, we started with the wells, since this is the point where the population gets the distribution of water, and most of them are in between 14 to 20 kilometers from the coast. So the coast has a big situation related with the population and also where the use of the natural resources. The other is the sinkholes, and we locally call it cenotes, because those are the ones that are used recreationally, but they are also related with some agricultural areas, and few of them right now, they don't have any use. So those are the ones that we use as control or comparison points. There are also some areas, and we call it Karst Lake, the halas, that are also related with big fractures, but also with endemic and specific species, like a specific type of reptiles and monkeys. Next slide, please. So the first one, we choose Tulum area because at that moment, Tulum was with a new set of 7 wells for the groundwater distribution, and because also the area is related with a reservoir for not only ecosystem, but for groundwater. So we checked for caffeine mainly to find out if it was an activity that was affecting mainly from the anthropogenical activity, but we also select the use of products for personal care, like sun blockers, and also the to avoid the mosquito bites, in this case, pesticide. Then next slide, please, was to compare in Puerto Morelos, this one is an area that is rising the population, but not only in touristic activities, but also in service, because a lot of people that lives there is working either in Playa del Carmen or in Cancun. So in this case, we have also an area that we call it a sinkhole road, because it's a lot of different sinkholes and a different depth. They have been used for recreational, but also for local activities. And in this case, we use the bacteriological quality, and we also evaluate the presence of caffeine. And we found that there is a difference between the distance and the depth of these sinkholes. The closest to the coast, we find more bacteriological activity, but the presence of the caffeine were more related with the size that the local were using. Next slide, please. Thank you. So since we find that situation where locals were really affecting more with emerging contaminants this reservoir, we went to a site what is very farther away from the coast, and also because in this case it's a karstic lake related with a specific populations, then they don't have too many sewage connections, but they are trying to raise the economy by inviting for the tourist activities. We did the bathymetry here to find out where it was the deepest and the shallow point on the lake, and what we found is that the distribution of caffeine indicate that in the shallow parts of this body of water is where there is more concentration of caffeine, and we think it's because also is related where the areas of the latrines that they have been using for the tourists, they are located close to those positions. Next one, please. So when we start analyzing these situations, we were trying to do the next evaluation with this groundwater. How deep these emerging contaminants can be found, especially because we have also the saline intrusion, so it's very narrow fresh water that could be in between to 1 meter deep. So we start checking in 3 different sinkholes, finding that there were antibiotics distributed in different depth. Unfortunately, we couldn't get more information because the pandemic happens and we were unable to get through these sites. So we think that this is an important point to relate with the different behavior of these emerging contaminants in fresh water, especially in groundwater, that is going to be used either by the locals for the groundwater distribution and use it in their house or in any other situation. And also because, as it was mentioned at the beginning, we are expecting a big rise of population, almost the double, due to the change in the infrastructure. The other situation is because in the north part of the peninsula, and do it also connected with the drain, is going to be more industry that is going to be able to use this water, but also to have the residuals used for
okay, summary, please.
Water. Next slide, please.
Summary, yeah, summary, please.
Thank you. Well, as just in summary, to the end of this talk, the emerging contaminants in groundwater, especially in the Yucatán Peninsula, that we are a dependent ecosystem, is not also related with the locals and the touristic activity, but also related with where is the groundwater. Is located closer to the coast or is inland. This detection led us to think about the more monitoring to promote more specific and more parameters. So these are the implications to distinguish between sources that will help to the stakeholders to make more strategies and protection policies. Thank you very much for your time. I'm sorry about the technical problem at the beginning of the talk.
Well, thank you. We can't control technology, but that was a wonderful presentation. And thank you very much, Rosa, for that useful information. We'll now be moving on to a talk by Benji Bronze. She'll be presenting on emerging contaminants in groundwater and their relation to recharge sources in India. Sounds really interesting because, of course, the source of the contamination is going to be most important for risk analysis. Thank you.
Thank you very much, and thanks for having me. Hello to everyone. So I'm presenting a case study from the city of Bangalore in India. Next slide, please. And the background to the study is we are all aware that emerging contaminants are becoming more and more ubiquitous in the environment. And we think that the more potential input sources we have, of course, the more crucial it is to monitor those. And there are a large number of Indian cities with populations over several millions, and Bangalore is one of these. So Bangalore has a population of about 8 million inhabitants, and there are quite a number of recharge sources in the city. So we have the more pristine rainfalls, of course, but we also have mains leakage. So this is the drinking water that's imported into the city. And then we have other surface waters such as urban rivers and quite a number of lakes. Bangalore is also subtitled the City of Lakes. And a lot of these lakes have, unfortunately, some inflows of sewage and other polluted water. But some of these lakes have also been lately what is called rejuvenated. So they've been fenced off and inflows have been reduced. And they look visibly a lot clearer, and part of the study, aside from the groundwater, was also to look at the difference between these lake systems and how they impact. Next slide, please. So the study, the setup of the study, which was undertaken between BGS and a number of local partners at Bangalore, was that we took 25 pre-monsoonal water samples in a snapshot study in 2018. Some of these samples are from surface waters, such as the Visha-Parvati River flowing through the city, and those lakes I just talked about, both rejuvenated and non-rejuvenated. But the majority of the samples came from groundwater, and then fewer samples were taken from tap water. And we undertook the study to get a first impression of what contaminants we find and what the difference between these are. So we had a broad screen, which screened for about 1,500 different emerging contaminants. Next slide, please. So first, the snapshot of the high-level results for all water sources. So in total, we found 126 EOCs with the highest concentration of 314 micrograms per liter. Across these samples, the highest group, if we group them to medical, veterinary, agrochemical, and so on compounds, the highest group was the medical veterinary compounds and the agrochemicals across all samples. And the surface waters were mostly dominated by medical and veterinary compounds. These are the surface water as in the lakes and the rivers in the city. But the tap water had more agrochemicals. And I should note that the tap water is imported from a different catchment, from the Carvery catchment, which is more of a rural catchment with more agriculture. But now coming to the bulk of this. So in the groundwater, we found 63 different EOCs. Within each sample, there were about 11 to 35 different compounds, and we found the highest concentrations of 3.5 micrograms for sucralose. Few concentrations were above 1 microgram per liter, just for 3 compounds, which was sucralose, as I said, then acesulfame, so another sweetener, and ibuprofen. Next slide, please. And some of the interesting results in here, and this refers back to my title, is that some of the compounds were only found in the groundwater and in some of the recharge sources. So the upper picture here, sorry, it's a bit small font, is a picture of the concentrations of trinexapac. Trinexapac is a growth regulator, so it's used in agricultural systems. And we found it exclusively in our groundwater samples and in the tap water samples. And the tap water samples come from a very densely piped network across the city. So there's a good indication for pipe leakage into the groundwater. And then we had other compounds such as sucralose that I mentioned in very high concentrations, and that pretty much showed up in all different samples. So it gave us a good overview of which contaminants come from this source, in that sense as well, how these sources and the groundwater as receiver linked to each other. There was a highlight here as well on the PFAS contaminants, which were quite dominant within the industrial compounds, just to raise that the PFAS concentrations were found in the city and quite high concentrations of almost 1 microgram per liter. Next slide, please. So to sum this up, we think that the broadband screening on groundwater can give you very interesting results in terms of groundwater age, because sweeteners were only introduced in the 2000s. And as I said, they can also link to distinct recharge sources, and this can be very useful to give us better information on the sources of groundwater, and also on the protection and monitoring effort of knowing what we want to focus on. That's the end of my talk. Thank you very much.
Thank you. That was very interesting. I really appreciate the interesting data that's come out of that study. We'll next be moving on to Malcolm Gander, who will be speaking on an analysis of the main categories of contaminants of emerging concern in global groundwater. Malcolm is the co-moderator of this session and is also actively involved in the IWRA as well too. So I'll pass over to you now, Malcolm, for your talk, please.
Okay, thanks, Bob. Hi, everyone. There's a need globally to simplify how to look at these contaminants of emerging concern. So that's really one of the main goals. Next slide, please. And we heard from Dan Lapworth about some of the common elements of emerging concern. We don't know the toxicity over all of these different categories of chemicals. By definition, CECs are unregulated, and they're not very well monitored. It's expensive to do the sampling and it's expensive to do the analytical testing. So I've broken this down into 6 categories. We all know about pharmaceuticals, that's 1. Personal care, household products is 2. Industrial chemicals, 3. Of course, we've been talking about PFAS, per and polyfluoroalkyl substances. PFAS is the best known so far. It's been under study for a good 20 years. It was actually first synthesized over 50 years ago. And it has wonderful applications, but unfortunately it's carcinogenic. So it has to be managed better, and we're starting to get better data. Number 4, flame retardants, enormously prevalent in the environment. They're in rugs and carpeting and furniture. 5, cyanotoxins, blue-green algae, algae in surface water bodies. There's varying toxicity with this, and it's fed by fertilizer and human waste and animal waste. So it's everywhere, and there's a toxicity associated with it, and it's complicated because there's many compounds, and for all of these 6 categories that I've come up with, there's another complicating factor, and that factor is there's the compounds themselves that have been pretty well defined for things like PFAS, like PFOS and PFOA, but there are also transient compounds or transformation products, which Dan Lapworth mentioned. And these transformation products or transient products, some of them persist in the environment, many of them fade away, but they're constantly being pumped into the environment, and we don't know their toxicity. So again, we really have to keep sampling and monitoring and try and do that in a consistent manner globally among countries. Next slide. So PFAS, like I said, very well known, synthesized in factories, used aquam, but also in things like Gore-Tex, clothing, carpeting, plastics, and it gets into the environment through surface water, it leaches into the groundwater. And importantly, which is one of the main points I wanted to make, is wastewater treatment plants globally are collection points for surface water, and a lot of the source areas where you have PFAS, it's getting into the surface water, it's getting into the wastewater from residences or commercial buildings, it goes into the wastewater treatment plant. And unfortunately, it's not stripped out in the wastewater treatment plants because that requires currently the use of granular activated carbon. The use of carbon, it's used in our households to varying degrees, but it has to be done on a large scale and it's very expensive. So we get around that potentially by controlling the source. How do we control the source? We identify it, we do research on the municipal level, but again, we have to sample. Next slide. So yeah, as I mentioned, CEC categories, we got the PFAS, it's in Teflon, Gore-Tex, sofas, carpeting, and the aqueous firefighting foam, wonderful product. But it has PFAS. PFAS has the carbon-fluorine bond. It's the strongest bond in nature. And it persists in the environment. And a lot of these PFAS chemicals are mobile, meaning when it gets released into the environment, it leaches down to the groundwater. It can travel 1 or 2 or more kilometers. Next slide. So we have pharmaceuticals, and then Another big category, like I mentioned, are industrial chemicals. We've known about the pesticides. There's this other product, 1,4-dioxane. You'll start hearing more about this. It's been around for years and known for years, but 1,4-dioxane is used as a purifying agent in making pharmaceuticals, but it's also used in the construction or the synthesis of plastics. So the stuff's everywhere and it's persistent, but it's not getting as much press as PFAS. Explosives. Now, we've heard about this for years. The actual unexploded ordnance in places like Vietnam, Cambodia, to a lesser extent, Germany from World War II. But it's not just the explosives themselves. These things, called TNT, this leaches into the groundwater. And many of these countries, they haven't characterized it at all, but it's carcinogenic and not as ubiquitous as PFAS, but it's a problem. Next slide. So here's a map of where a lot of this unexploded ordnance is. I just wanted to mention that because this is a largely unknown issue. Next slide. So the pharmaceuticals, we've heard more and more about this. There's a lot of studies coming out of academia in Africa and Europe, as well as the US and South America, where we're starting to do specific studies. We saw some studies about pharmaceuticals in groundwater and the effects of the pandemic, how there was some increase seen in some of the pharmaceuticals over the pandemic and so forth. But I mean, it's everything, antibiotics, analgesics, and so forth. So, you know, again, we've got to characterize this stuff. Next. Personal care, household cleaning products, literally hundreds of products. These are additives, ingredients, shampoos, sunscreens, as we heard down in the Yucatán. It's all over the place. Mercury, and of course, PFAS, again, is in some of these personal care products, and also in some of the cosmetics. Next slide. Flame retardants, enormously prevalent. Again, a very good product, adds to consumer safety, but we need to think about where we're disposing of old carpets and furnitures and whatnot, because this stuff is getting into the landfills and it's leaching down into the groundwater. Next slide. So cyanotoxins, less well-studied, ubiquitous human and animal waste are the sources and the fertilizer. 70% of the world's groundwater is used for agriculture. A little under 50% of global groundwater is drinking water. And the groundwater and surface water is being subjected to these cyanotoxins, and their toxicities poorly understood. Next slide. Next slide. Yeah, and the last one, these are literally hundreds of materials in products. They encompass metals, they encompass carbon fiber, and they're on the order of 1/100th of a millimeter. So more information needs to be disseminated about this. Next slide. Next slide. And as I said, it's convenient to talk about these 6 categories. Thanks very much for your time, and happy to answer questions. Thank you. Thanks, Bob.
Thank you, Malcolm. And we'll take questions in the chat, in the Q&A box, or also we can take questions if there's any at the end. But Malcolm, thank you very much again for a very informative talk there. We'll be moving on to Tamaris Ferreira. who'll be presenting on microplastics in urban soil and groundwater in Brazil. I think we'll find another very interesting case study here. Thank you very much.
Good afternoon, everyone. My name is Tamires, a student at Federal University of São Paulo, and I will present my research developed together with Ricardo, Décio, and Juliana, whose theme is microplastics in urban soil and groundwater in the city of Bauru, São Paulo, Brazil. Next slide, please. Microplastics, or MEPs, are synthetic polymers derived from petroleum, with sizes that range from 1 to 5,000 micrometers and shapes like spheres, films, fragments, and fibers. Next slide. The objectives of this research were characterize soil type, characterize the MEPs in soil and groundwater samples, relate the occurrence of MEPs with the environment properties, and discuss the potential source of MEPs in the site. Next slide, please. The soil and the water samples were collected in the city of Bauru in São Paulo, Brazil, where groundwater is used for public supply and where there is a historical contamination of groundwater by sewage. The points in yellow were the boreholes and the blue points indicating the monitoring wells. Next slide, please. The methods were divided into 2 stages. First, we collected the soil and water samples at the site, and then we did the laboratory analysis to characterize the samples and identify the MEPs. Next slide, please. In groundwater, we found that MEP fibers were dominant with sizes mainly from 0.063 to 1 millimeters. Also, there was a predominance of colored MEPs. Next slide, please. In the soil samples, we only found fibers with higher concentration at 0.5 meters depth, and also with a dominance of sizes 0.063 to 1 millimeters, represented by the orange color. Next slide, please. This image shows a summary of the main results obtained. In red are the results for soil, and in the blue, the results for groundwater. A high occurrence of fibers was observed at a depth of 0.5 meters, where there is a higher content of clay and organic carbon. A second expressive occurrence of MEPs are between 2 and 2.5 meters depth, where the saturate zone is located and there is a higher iron content. Next slide, please. In summary, MEPs were identified in soil and groundwater, predominantly in smaller sizes. Fibers were dominant, although in groundwater some fragments were also found. Next slide, please. You can back. Thank you. There was a clear distinction between the saturated and unsaturated zone in relation to the MEPs colors. In the saturated zone, there was a predominance of colored fibers, while in the unsaturated zone, there were mainly transparent fibers. This, combined with the presence of fragments in the water, indicates that the source of contamination for the unsaturated zone and saturated zone might be different. As can be seen in the conceptual model, for the saturated zone, possible sources of contamination include atmospheric deposition, inadequate disposal of solid waste with consequent runoff and infiltration into the soil, in addition to flood events on the Bauru River. For the saturated zone, the sources of contamination would be sewer pipe leaks and old septic tanks. Next slide, please. I thank my colleagues at Unifesp and USP, FAPESP for financial support, and UNESCO IWRA for the opportunity to present my research. Thank you for all.
Thank you for a very informative talk. That was quite interesting. Thank you. If I could remind all the speakers, there are some questions in the Q&A box, and if you have the opportunity, you can respond in writing back to those questions as well. We'll take the last speaker of the session, Melissa, who jumped in very quickly earlier on. She'll be presenting on the impact of changing tourist numbers on sunscreens and antibiotics in groundwater during the COVID-19 pandemic in Mexico. Thank you.
Well, thank you very much for having me today. I'm Melissa Lincheski. I'm from Northern Illinois University. And thank you to Rachel and Malcolm and Rosie. You guys really set up my talk really wonderfully, and I'm glad I'm last here. So next slide. So as Dr. Leal mentioned about tourism in Cancun, this is one of the biggest drivers, and even around the world, when people are thinking about economic expansion, they're thinking about tourism. And so one of the things that we really wanted to look at was, how is tourists and tourism impacting groundwater and groundwater resources? And so we're using Cancun as a study site because it is one of the few places where this is really the only drivers of groundwater pollution is tourism. Next slide. So, and as has been mentioned before by Rachel and Rosie, that karst systems are very easily contaminated. And so they can be contaminated by tourists, by the residents or the local people that are in here. And this can be, especially the cenotes down here, the sinkholes down here are used for swimming. And so what is this tourist activities into the groundwater going to look like in these regions? There's also wastewater. How do we treat all the water, especially when you're in very rural areas? And so what impact does that have on a karstic situation? Next slide. And as we know, COVID happened. And so when COVID happened, all of a sudden there was no tourists here in Cancun. So we dropped off to nothing. And, you know, over the years, we've been really trying to like separate out what are the locals versus tourist activities. We tried like high season, low season to try to separate those, but then we also had a lot of issues with climate in there. So this natural research happened, and we're like, okay, so let's really see what happens when there is no tourists inside of a location such as Cancun. Next slide. So this really filled in some natural gaps, and what we were using to look at this was sunscreens and antibiotics. Again, as mentioned before, these were proxies for human activity. Sunblocks around the world are starting to be banned because of their impact to reef systems, and we have a very large coral reef system. And antibiotics and antibiotic resistance are, you know, coming in when people are doing activities, wastewater in there. So we were using those as our tracers in here. Next slide. The other thing that we were looking at was there was a new wastewater treatment plant that was being connecting a lot of the septic systems right on the beach. So one of the things we wanted to look at was, what is that impact of actually switching from using septic systems to a wastewater treatment plant? Next slide. So our study area was here in Cancun. We, on the left side is our study sites. So we have a mix of beach locations, these cenotes, as you can see in the pictures, of people swimming in them or no swimming, what happened during COVID. We also have some cenotes that are only used by residents or not used. So we had a very wide variety of sites, from very large interior all the way down to beach samples. So next slide. So we studied we collected water during the pandemic. So this was done quarterly through the pandemic. That was as much as we could get out to some of the sites, what sites would let us in during the middle of the pandemic. And then we also studied during, as the tourism was coming back up. So we had Rosie go out and sampling, and then we also had a National Science Foundation research experience for undergrads come in and sample throughout these different cenotes. We looked at different beaches, cenotes, and recreational areas, and then we analyzed all the data on an LCMS. Next slide. So what were some of the results that we got? So for sunscreens, again, on the left is the map of the locations, and on the right, we have our inland locations, and then we have our beach site. And so this is an accumulation of all sunscreen, all the samples that we sampled throughout the entire time. One of the sites we have lower inland, and then the beach was very high because they were still on septic systems and also beach activities. So we do recognize that sunblock is being used a lot during the beach, and that's having a major impact on the coral reefs. The other site that was high was VL. It's a very tourist activity cenote, and that was one of the sites that I showed with all the people in it. Even with that, we saw a lot of sunblock getting into the groundwater. Next slide. So for this slide, it's a little complicated, but I'll go through it. On the left is the percentage of sunscreen. So this is all the different sunscreens that we looked at, how much was there of each of the different types of sunscreen. And on the right-hand side is the total concentration of all sunblocks together. Starting in the upper left, that's March, right as the pandemic was occurring. And then these are the different months that we sampled, ending in July of 2021, when tourism activities were pretty much, not full, but pretty good. So what do we see with these different sampling sites? So what we notice is that during the height of the pandemic, when nobody was here, we still see sunblocks and sunscreens inside of the groundwater resources, but we don't see a lot of variety, showing that the locals and the residents of the area are still using sunblock. It's still found in makeups, it's still found in everything. We're still finding it in the sunblock, but we're not seeing a very big variety. If we go to the last part of this and you look at the changing colors on the left side, you see that what we're having is a much more diverse sunblocks coming in. So as the tourists are coming in, they're bringing in these different types of sunblocks. A lot of them that are banned around the world are coming in here. People are bringing them with them. And so we're seeing a large variety of sunblocks. On the right-hand side, we are looking at the concentration of it. And as you can see, the concentrations are pretty small compared to the beach sample, which I'll show in a second. And so we have a variety, even though the concentrations didn't really change when tourists come into there, what we're really seeing is the variety. So showing that the locals or the residents here are providing the largest concentration of sunblocks, and tourists are providing the biggest variety. Next slide. Next is our antibiotics. So we have inland and then beach. We're seeing VL, which is our high tourist activity cenote. And then we're seeing inland at LL and Domo, those are very high residential areas. And then the beach area, again, where we were switching from septic systems to a wastewater treatment plant. You're still seeing that. Next slide. So we looked at, this slide combines the percentage and total concentration. So if you look again on the upper left corner, this is during the pandemic. We're seeing a wide variety of antibiotics and high concentrations. Why is that? Well, during the beginning of the pandemic, none of us, people knew that this is a virus, but, oh, maybe I should be taking antibiotics. And so people were going to a lot of these stores and just buying antibiotics. We're seeing antibiotics that are only used for animals in these samples. So there's a lot of high concentrations of antibiotics when there's no tourists here. But also what we see again is that as when tourism comes back, we're starting to see much more variety of antibiotics. A lot of antibiotics that people are using, such as ciprofloxacin, are mixed in there. Next slide. And then the drainage efficiency, we were looking at adding that wastewater treatment plant. Sunscreens are on the left, antibiotics are on the right. And what we're seeing is as soon as they put in that wastewater treatment plant, we're starting to see the decrease in the concentrations of sunscreens and antibiotics going into our coastal communities and impacting the coral reefs. Next slide. So our findings are unique. It's one of the ways that we can try to tease apart the different types of communities that might be causing the contamination. So tourists do contribute to a diversity of contaminants in groundwater, especially to sunblocks. So they're bringing them in with them in their makeup, in their sunblocks, even though a lot of the places around here say use reef safe, such as titanium dioxide, but we're not seeing that. We're seeing that people still bring them in. We witness people on buses saying, I'll just put it on in the bus before I go swimming, even though they want you to rinse it off. But the locals or the residents of the area were really adding to the diversity of antibiotics, especially during the pandemic into here. So we see some differences between those. And that wastewater treatment plants, again, are a great way of removing a lot of these contaminants before they get into our groundwater. Our next step is adding in our 2022 data, which is still finalizing being analyzed. And it also includes, like, as tourists are coming into the cenote during the day, does that concentration increase in these cenotes of the sunblocks and antibiotics? And we're also looking at different types. So we've got some future research on this. Next slide. And thank you very much. This research has been sponsored by the National Science Foundation. And I'll take any questions you might have.
Well, thank you very much, Melissa. Well, unfortunately, we've run out of time for questions during this session. A little bit of challenges with our connections and so on and so forth. I'd like to thank all of the speakers in today's sessions for some very interesting and thought-provoking presentations on CSCs and groundwater. I'd like to thank co-moderator Malcolm and also our rapporteur Dalia from the IWRA for the efforts and times that have been put into this. Before I hand over to the IWRA, I have a few more things to say. That first of all, we've collected written responses from presenters in the chat boxes, in the Q&A boxes. Any remaining questions will be placed on the conference website. Remind you that there's an excellent selection of conference posters. So if you go to the website, don't forget to go to the posters. They're fantastic. Something to do tonight when you're having your lunch, your dinner, or tomorrow morning at breakfast. If you have any questions at the posters, you can send an email at the online.conference at IWRA.org, and they can contact the poster authors to respond to your queries. And the PowerPoint presentations you've just seen will also be made available soon on our conference website, along with the video of this session as well too. With this, I'll hand over to the IWRA, to Ignacio, and I thank everyone again for the attendance and for the presentations.